slides, and it would be nice to not have to look at that muted screen here. So you're welcome to follow along if you'd like to do so online, starting now. Okay. So I have a Google Live event on my YouTube channel, defect counts, text and reproduction reports, traceability and software. Okay. And you should be able to follow there if you'd like to see it with better color fidelity. Okay, so today I am going to cover some materials that we actually started on in a previous lecture. We didn't get a chance to completely finish. But it was, you may recall that I asked you to ponder a slide, and it was in fact this slide. This slide shows it depicts a history of bug finding, and particularly the cumulative count of defects found per 1,000 lines of code in the y-axis, for a set of NASA space probe projects. These occurred at different points of time, but for each one, it's showing on the x-axis the time since sort of the project was in a, I believe, a compilable state, and this is number of weeks of time as time went on that the project was undergoing testing. Testing and debugging. And each line is a different project. So to give you a sense of scale here, this is approximately 1 year is about what I'm sort of highlighting here. So it's a fairly long time scale of several years, reflecting the fact that the space probes, which can cost hundreds of millions or billions of US dollars to create, are larger scale investments, and the need to make them absolutely robust prior to launching at the risk of otherwise losing that investment. So we're seeing here defects then over time within this diagram for 3 different projects. Are there certain components? So I'd ask you to notice some patterns within these lines. Does anyone want to comment on one pattern that you'll see? Yeah.
Projects that found bugs early had fewer total bugs.
Okay, that's nice. Very interesting observation. So here, this one, which happens to be yellowish color for those following on YouTube live events, this one that goes up and then sort of plateaus here. It's a lower density of defects per 1,000 lines of code. The y-axis is showing density, so bugs per 1,000 lines of code rather than strict bugs, but it was a lower density of bugs, and they apparently found those defects earlier. Okay. How about another pattern? So I like that. One pattern that's in common for all of them is the lines only go up because this is cumulative count, and it's so over time, if you're not finding any more, it'll plateau, right? Flat here. Otherwise, it will rise as you find more ones. So that's not a surprise that they go up. It's almost it's baked into the nature of this graph. But what other patterns might you see?
So long as you keep testing, you'll keep finding more defects.
Okay, good. There seems to be on an ongoing basis defects to be found even after years. Yeah.
The bugs are all found in bursts.
Okay, they're found in bursts, and that's. I really think your name?
Mitchell.
Mitchell. So Mitchell has highlighted a very salient point here. So you'll notice that that things kind of go in this staccato sort of form, or this punctuated equilibrium form. So there'll be a set of bugs found very quickly, set of defects, and then it will kind of undergo a period of sort of more sleepy period where not much is being found, and then it will shoot up again, and then it'll sort of stagnate and then shoot up again. And you see this across projects, right? Like the same thing here, sort of goes, and then you'll see a burst essentially. And even this one here with the Galileo probe, this sort of longer one here, you see it kind of going up at the end in another burst. What do you think that might reflect?
Yeah, that when you found one bug, it was there and fixed an issue that was related to another bug. So when you fix that, you immediately point to another bug.
Okay, so really, really good point. Yeah. I slowly learn. Sorry. I'll feel on top of it just when you leave. It's horrible. So that's a key point. Defects are not independent. And this matters a lot. It matters for testing because for several reasons. One of the big ones is that we may not be able to find another defect until one defect until another one is fixed. Our path through the program could be blocked by a defect. And until that's fixed, we can't get to where we need to fix it. Or another way, what's another way there could be a linkage between them?
Fixing one breaks another.
Yeah, fixing one breaks another. Is there anyone in this room who's ever been in that? Anyone not been in? Okay, don't be hired. No, so I think we've all been in that situation. You squeeze the balloon here, it pops out over there, right? And it's not fun when you're in Sphinx at like 11:30 in the evening, and you fix this and it doesn't work here, and you fix that and it doesn't work over here. Unfortunately, the truth is that projects have what are known as fault feedback ratios that can be pretty high. It can be above 0.3, meaning for each bug you fix, there's a 30% chance roughly that there'll be a bug introduced, or 0.3 bugs will be introduced for each one you fix. That's pretty sobering. It's especially sobering if you're close to shipment and you have a defect that you'd like to fix, but you've got to be really careful because of this. Why? Okay, so you have this defect. It's maybe one that's pretty obvious to the user. Why might you have to balance this thing about fixing one bug might cause a different one explicitly? Suppose you're 2 days away from shipping the client.
If you don't have time to test it, and then you don't know if the bug you introduce is worse or better than the one that you're working on.
Well put. Well put. So it's kind of the devil you know, the devil you don't know, right? The devil you know is this one that you see. You can document it. You can set expectations on the part of the client at days ahead of time. That look, we've got something we feel is pretty good. There's one thing we've got to warn you about, but we can have a workaround for it defined. We can have a demo that sort of works around it, and etc. But if you go and you fix it, you don't know if another one's going to come. It could be worse, or more to the point, we may not even know about it. In time to work the demo around it, to set the expectations on the part of the client. We don't know what we'll end up with, right? And critically, we may not have time after fixing this to undergo another round of testing. So we're kind of driving blind. Whereas at least with this one, we know what we've got. So this is one of the big reasons certain bugs don't get fixed. They get documented and so on. So that goes on as well. Another thing that you get with bugs being fixed in bursts is, or excuse me, of one depending on another, is that it can allow for slower progress on the debugging front. One bug has to get fixed in order for another to show its face, not because it blocks that way into the program. It's just things are so screwed up because of the first bug with respect to the data and so on, that it isn't clear that this more subtle bug becomes obvious. It brings it to the fore. It's a blemish that wasn't obvious before, now it is. So defects are tied together, and that extends our project sometimes because we think we could finish, fix them all in parallel. We can't. We have to wait till one, fix another till another one becomes obvious. Okay, so that's a feature of this. What's another reason, though, besides dependency on defects, that you might have bursts in how defects are found? Yeah.
just within like the software processes that they're using.
Good, good. So maybe we could, so absolutely a key issue, it turns out. Can we expand on that a little bit more? Yeah.
I'm not sure if it's exactly the same, but if the software is being used more,
Okay.
bugs get found more often.
Okay. Okay. So we have users using a certain component of the software that allows it to sort of that area to be tested finally. Yeah, that's possible. Other things? How about testers learning? Testers learn. What do they learn?
The test themselves.
How to write the test, yeah. And when a new, so I would say testers learn about what types of bugs are out there. You observe one bug and it gives you ideas for other similar defects, right? So you see a bug associated with how you're treating permissions in this area of the project. Maybe it clues you into the fact, oh no, now we've got to deal with that in 3 other areas, right? There's a similar defect. Let's test for it in 3 other areas. Or, you know, we have this buffer overflow in this area. Now we need to look for the comparable error elsewhere. Sometimes you get new testing tools being deployed. So you initiate coverage testing, and you end up in the process of pushing it to cover new areas of the program. You find certain defects there. Sometimes you'll run it with a heap checker, and you'll find a couple different bugs because now you're using this heap checking product or whatever. You start stress testing, and you find a couple bugs in the way there. So it's, again, as Ryan said, it's driven by testing processes, the tools involved, the processes undertaken to explore those tools, new test suites that have been rolled out, etc., that can find things. So bugs come in flavors, and once you've seen one of a certain flavor, often it allows you to see several. And that was a sizable thing during these projects. They sort of realized, oh, we have that sort of thing going on. Okay, let's look for more cases of it, and chances are you'll be able to find that. Okay, so years in the making, still defects. Defects come in bursts. One defect sometimes blocks another from being discovered. And yet some projects end up better off than others, finding it sooner and having lower cumulative count of defects. It should be sobering for those in the room because this is many years, right? Somewhere up here, we're in kind of the 5-year range for debugging that project. I believe we both come to the understanding that you'll be in this class for fewer than 5 years, for better or for worse. Okay. So I had talked earlier about stages in a defect's life or system trouble incident's life. I do want you to be clear about these things. You remember there's kind of undiagnosed defects, reported defects, active bugs after it goes through sanitization, where we basically weed out duplicates. We weed out ones that are obsolete, ones that are based on misunderstandings, etc. Triage to get important bugs, assigning them to different developers or self-assignment by the developers to a case where they believe to be fixed, but they still need to be confirmed by the test team or the original reporter. I want you to be confident about that report, and I would note that it's this undiagnosed one that in some ways is the most important one to drain, right? Because there's a lot that are here that we may not know about. Here we have a count. Here we have a count. Here we have a count. Typically, we have a count of number belief fixed, what have you. But it's this number that we're often unaware of. And in a later lecture, we'll be talking about that. Okay. Active bugs will sometimes include those that are judged too risky to fix, or those that haven't made it too important bugs. We haven't triaged them. The too risky to fix, we'll just document them, set expectations. They're defects that are too minor to merit cost to fix, right? They're they're minor things, and we don't have time to fix them. And especially if time is short, we may leave them. Okay. I want to talk a little bit about defect reports. So all of the projects here are using defect tracking in some form. There are teams that use Trello for defect tracking and sort of feature requests and so on. I'd be cautious about that just because if you look at professional products, Jira or Redmine or Bugzilla or what have you, they're really quite specialized to this area, but you can do it with Trello if you follow a structured process. And you really want to think about what you document in these defect reports, okay? These are really system trouble incident reports. They might or might not be, in fact, defects with the program. They could be based on misunderstandings or other things. But broadly, you want a title. You want a priority and severity, which I'll come back to, some way to reproduce it. Why would you include a reproduction formula here? Why include that? Yeah.
Makes it much easier for the administrator to test specifically about that one bug.
Yeah, it may take you time as the bug reporter, but it will save a huge amount of time, quite likely, on the part of the person trying to fix it. Maybe more to the point, or equally important, at least, is it might lead to them really giving it credibility and tracking it down rather than just dismissing it as a misunderstanding. So this is really important to say something about the reproduction formula, how to reproduce this. Okay. Who's been assigned it? If that's something the dev lead, or excuse me, the test lead will do, excuse me, dev lead to fix it, person assigned to here to fix it, they might assign it, or maybe a self-selection and someone grabs it. What area of the project? Person opened by. Why would you record who opened this ticket? Who created this ticket? Who reported this? Why would you want to report that?
To get more information from them?
Yeah, because you want to ask them, I wasn't able to reproduce this. Could you help me with it? Or it wasn't clear about this aspect of the description. What system were you working on at the time? They're not using a containerized environment. So that's one reason. What's another reason?
Let them know that it's fixed.
Yeah, to be able to let them know that it's believed fixed. And often you will look to them to make sure that, yes, you fixed it per their expectations. Because there's a huge amount of misunderstanding where one person thinks it's fixed and it's not fixed. They didn't fix the real thing they were talking about, or they didn't fix it in their environment. It's still there in their environment. Or they never even reproduced it, and they decided it was fictitious, but in fact it is there, as viewed by the person who reported it. So you really want this person to be the one who marks it as truly closed or at least resolved. Okay. And you notice the resolution. It may be fixed. It may be postponed. It may be a duplicate. Well, maybe just we've decided this is not going to be fixed. The type, is it a regression or is it a regular one? Is this an older issue coming back, or a component that used to work now failing, or is it a sort of more regular bug? And then triage, sort of accepted, rejected, if it's not going to be fixed. Now, the ones I want to speak most about, though, or highlight here, are priority and severity. Okay, these are different. Severity is all about, and this gets back to sort of risk management. Severity is about how serious is it if it happens. Put aside how likely it is to happen. If this thing happens, how serious is it? And you can imagine different levels of severity. Data loss is a security issue, major functionality doesn't work, minor functionality. But also, it renders the system inoperable for the time, freeze or halt, right? Crash. These are very high, those are very high severity things. And you want to distinguish, or is this a matter of minor functionality, okay? So that's severity. If it happens, how serious is it? Priority, by contrast, is basically classifying how important is this to be fixed. And it takes into account severity, but it also takes into account the likelihood that it will be encountered for our users and their situation. So it's taking into account the fact that there may be something that's really bad if it happens, but it's very unlikely to happen because it depends on old hardware, a very unlikely confluence of circumstances, types of functionality that are almost never used these days within the system or what have you. And here, really, you're saying, okay, how important is it for us to fix? Is it a must fix, fixed as allowed, but desirable, but it's unlikely or extremely improbable? So what I want to be sure is that you folks are recording priority and severity for things, and don't assume they're the same. If it crashes, you got to evaluate: is this really important for us to fix based on how likely it is to get through? Yes, Mohammed.
Would it be valuable for us to actually record also if it's a breaking behavior or not? Meaning that if the result of fixing this defect is going to cause a change in the behavior of the system,
Good point.
Not.
Yeah.
Change in behavior.
That would be actually very nice to be able to say. It's not listed here. It might be something you add to notes, but it'd be nice to have a field for that. I will readily admit. In other words, fixing this might change the functionality anticipated. So it breaks backwards compatibility, or it breaks the expected functionality, and as such, it might cause a change in elements of design or documentation, etc. Yeah, so it's a very good point. And it's different than just it being a regression, where this is temporarily damaging functionality that used to work, but now once we fix it, it'll be okay. Yeah, Owen.
At the start of the slide, you mentioned like some other tools like Jira.
Yeah, Redmine.
When would you choose to use those instead of just using like GitHub issues to track people?
GitHub issue tracking is okay. I would put those in sort of the same level of functionality. Jira and Redmine, I think it's Jira actually includes a significant amount of other project management tools beyond what's provided with GitHub. And it's more sort of designed for sort of providing, as I recall it, providing a project management console or sort of capability for a project as a whole, whereas GitHub has sort of the issue tracking. I view it as kind of tied in with the repo and the continuous integration, but it's not a complete project management suite. So some of these others tend to be a little bit more inclusive. But there's no question, Owen, that per your comments, that these days, what used to be separate products for doing this sort of defect tracking are increasingly being put into things like GitLab, GitHub, etc., where it's very naturally tied in, because then with defect tracking, you can relate it, say, to a check-in, right, to a commit that was done. You can say which commit later was responsible for fixing it, that I claim will fix it. And as such, or which merge conflict, for example, might have led it to be a regression again. So the move is definitely out there to use them in conjunction with repos and GitHub issue tracking. I view as a very nice solution. So I have no problem with that being used, but you should be aware that that these other products like Jira do provide a broader suite of sort of project management functionality than is available on GitHub. Okay. Yeah.
Another point on priority.
Yeah.
Not just the probability of it happening, but also considering who it happens to.
Yeah.
So if it's an admin versus a paid user versus a free user.
Good point. Good point. I like that. So there might be some of those users who are particularly vulnerable in the sense that they're going to be unable to deal with it or be unable to easily report it, who you might not hear back feedback from about this or won't have workarounds available to them. So yeah, I like that. So in addition to sort of area of the product, you're really talking about sort of elements of the user community that it affects. So I like that. These are good. And my recollection is, and I could be off, but I'm pretty sure some of these other systems allow you to customize what fields you have here. So you can have for your field, if you have like a hardware software project, you might put in a field, you know, is this a firmware issue, a hardware issue, a software issue? And in other words, customize these fields. These are not catch-all fields that are always applicable, but these are fields a lot of projects have found very useful. Going back 3 decades, I remember using this in the late 80s when you folks were smaller. Okay, so pretty good bug reports. Creating these bug reports is not free, and I recognize it takes time. It also saves time and it saves credibility for getting it resolved. So it behooves you to do a little bit of, before firing one off, it behooves you to do a little bit of work. And I'm going to list some things here. I'm not saying these are required, but I'm saying you should think about them. You know, is it always reproducible? Do a structured exploration to try to, between that and sort of to isolate it, to try to pare it down from a long series of steps that you have to undertake to a short series. I mean, I think we've all encountered bugs at one point or another in third-party products or our own or in-house ones, where fundamentally we get something unexpected, and then we find that actually we can create it, we can cause that to happen in a much more simple way by fewer steps. And really that's desirable. It allows the whole testing process and debugging to be much more efficient. If we can wheedle it down from 15 steps to 3 to get there, we don't need this, we don't need that. It helps us more quickly reproduce it. But what else does it help with? Think about debugging. What else does it help with? Have it shown with, say, 3 compared to 15 steps. Yeah.
Increases the likelihood it's going to be more severe. The easier it reproduces, the more probable it is to occur.
Okay. So yeah, you might be able to make it reliably occur, for example, in fewer steps because there's less else going on, which might affect whether or not it occurs. That can sometimes be the case. Like if it's a
what I mean is instead of saying it happens on say Windows 95 32-bit with 2 gigs of RAM installed, it's like it's Windows NT based.
Yeah.
So it's much more likely to occur in the real world rather than it's a rare occasion.
Okay. Yep. So you may find the fact that, in fact, you may discover the fact that it's actually hits a much broader set of cases, right? There's actually a generality here, so that's important. Absolutely. What's another reason for debugging, especially? If you can reproduce it in 3 steps rather than 5, that will be useful. Yeah, it saves you time, right? Each time you're going to be debugging it, you want to and often as part of debugging it, you're stepping it through, or you're trying to probe, different aspects of its behavior, and you may have to run it 10 times. And if you could pare it down, so each of those times you run it, instead of having to set it up for 20 minutes before seeing it, you can only set it up. All you need to do is, set it up for 4 minutes or 3 minutes. You could have much quicker cycle for debugging. So that's good. What's another thing? With debugging, often you're developing hypotheses for what's going on. Ladies and gentlemen, this is, gosh, there's several classes I would love to fold into our curriculum for you folks, and I've suggested these before to our program, and one of them is actually, of course, in debugging. Turns out that studies have gone on looking at effectiveness of debugging by different developers, and there's literally a factor of 10 times that is manifested. So in other words, there are developers who can reliably debug things 10 times faster than others. And it's not just a matter of smarts at all. I mean, you might argue that's a component, but a lot of it is method. It's like, how do they go about debugging it? You know, one of the key steps is, and these are documented in a variety of books, if you folks are interested, is to develop hypotheses explicitly for what's going on, and you systematically investigate those hypotheses. You make notes of the evidence, and you iterate, refining your hypotheses, ruling out hypotheses. That's not all there is to it. There's actually a lot more than that, but it helps. And the deal is that if you have fewer steps to reproduce, you're narrowing it down what the set of possible working hypotheses are that could lead to this, because you're finding fewer things are needed to cause it. So you might initially think, oh, one of those previous steps, so the 15 to get to there, is needed, and you think, oh, it involves this or involves that, which are involved in those previous steps. But if you can do it in 3 steps, you start to develop clearer, simpler hypotheses for what gives rise to this. So, ladies and gentlemen, being able to reproduce things sooner and with fewer steps helps our debugging processes, okay? In addition to being able to recreate it. And along with this is isolation. You sort of figure out, oh, we don't need to do this before it. We can just do this and it will happen. And I don't know about you. Probably you folks think I should get out more, but I actually really like this process. I like taking a bug that only comes up in obscure conditions and just iterating on it until it's like I can just make it crack. IBM had a team. It was called the Black Team. Okay, it was a team of crack testers, and they really played the part. Probably more so than I'd be fully comfortable with if I'd been their manager. So they kind of had a little bit of almost a goth thing going or something like that. They would dress in black. And programmers would, so the developers would submit their code for testing. And when they encountered the test team members would often, you know, cackle. And literally, like within 30 seconds of them submitting, they just break it. And they basically like, you know, I'm gonna crush you somewhere. You know, look at this, and they'd crush it. And they had a reputation for sometimes bringing developers to tears. You know, who've been working for days on this thing, and they bring it in, and you know, they just crush it within 2 minutes. Like, this is not robust software. Look at this. I'm going to crush it. Well, okay, I won't say it. But and they'll crush it in front of them. And that was not an accident. I mean, it wasn't that they had magic on their side, that they were doing incantations. The issue was they recognize certain types of vulnerabilities and they exploit them. They aren't unique in that regard. Certain professors are known to have their ways as well. But the fact is that a good tester can really sort of zoom in and arrive at a nice, quick, reproducible way to reproduce a bug, and that's a contribution. It's a useful thing. Making developers cry is not a very useful thing in my experience. Okay, so you know, here, a lot of these earlier stages are sort of simplifying, generalizing it, isolating it, so we know what it doesn't depend on as well as what it does. See if it, why would you see if it exists in other versions of the software? Why would you go through the bother bother of seeing if it was in the previous version, this bug.
See if it's new.
Yeah, you see if it's new. And why would you want to see if it's new?
Maybe whatever commit came along with it is what broke it.
Exactly. It gives you a big hint. Talk about hypotheses. Gives you a big hint for what might be there. Or if it is in the previous version, it clues you. You don't want to be caught up by red herrings, right? That you think it's a recent change, but it actually goes back 4 versions. It starts to give you a clue about, oh, it came in back then. Gosh, we didn't even have all these areas of the system back then. It starts to clue you into what it might depend on, right? So figuring out if it's in earlier versions or is this a new version, it's really useful. It takes time, but it saves time. And that's a lot of the deal with software development and software project management. We're so busy doing things and throwing it over the fences to others that sometimes as a project as a whole, we waste time. Because a bit of time invested on my part can save others hours potentially. Here, comparing with other versions, really useful. If you can have a Dockerized version of past versions of your software that you could fire up and see, is it in that? Is it in that previous version? Is it in this one? It could really help narrow down things. Summarize the above report, condense it, neutralize it, folks. The real problem here, and this is a problem that transcends many projects out there. It's unfortunately something that you see quite widely across the industry, is that there is often a tension between developers and testers. And you saw that with IBM's Black Team, right? They make the developers cry. And it's not unique to that team. Developers generally don't like to see their code break. But it's more than that. Developers test their code, but they often test it sympathetically. They test just to make sure it works. Looks good to me. Time to commit. Move on, right? In some perverse cases, they may sometimes pride themselves as, I pump out 1,000 lines a day of new code. And they get so caught up in that they don't realize the amount of effort that it's really worth it for them to put into to testing it and quality. And the issue is that they're not really testing it with an eye toward breaking it. With testers, they want to find the defects in it. And generally, they will find them. And they will find them much more effectively often than the developer. Because the developer wants to move on. They want to get it off their plate. They want to show that it works and move on. Whereas the testers are out there to find, okay, where are the defects here? Now, when a tester reports a defect, it can be a situation that can lead to defensiveness. Can you imagine that? You've been working all night. You're really sweating the details of this algorithm. You feel really good about it. And then you go to sleep late. You wake up in the morning and there's a defect report. Doesn't handle all these cases. And generally, it's not a great way to start out your day in terms of your mood. And it can lead to recriminations between the two. And you may think that this is just a little sideshow in the human theater, but these things can get in the way of effective communication and working together. So what you want here, you can't perhaps head off all chance of this, but what you can do is at least make bug reports not sound incriminating. They don't sound gratuitously nasty. They don't sound like in your face. That nice code you pumped out, time to go back to the drawing board, buddy. You don't want that. You want to have it be neutral. And you may think it on and spending time on this, but it's a real part of the human theater of software. And by the same token, developers you'll sometimes see kick things back at testers and say to them, you don't understand how the software is supposed to work. Basically, stop bothering me. Or you'll see them kick something back in a way that is quite unfriendly and say, this is by design. Essentially, go back and figure. So put some time into neutralizing things. And if you're a developer, don't just throw things over the fence and expect them to be defect-free. It's part of the job to kind of expect people to point ways to improve your code and view it that way. It's ways to improve your contributions here. Okay, so reproducing bugs, reproducing defects. Generally when you're trying to reproduce things, you want to be careful to reproduce in a way that doesn't destroy the potential to reproduce it again. So if you have a system that depends on data that could be modified during a test, make sure that you can get back to this original state. Why would you do that? So suppose this test is going to destroy data. Why do you need to get back to this state again?
Yeah, if you need to verify it's been fixed, but the data isn't there to get you to that point.
Very good example, Nick. And even before that, you want to make sure that you can reproduce it again, perhaps try it a few times. And if in the process of reproducing it, you lose the ability to reproduce it again, you've really shortchanged yourself. So, you want to make a copy. And if you're doing exploratory testing, and this is a shout out to all you testers out there, and even for the devs doing, doing some exploratory testing, if you're doing testing that's a little bit more open-ended, try to make a note or otherwise record what you're doing. Maybe you log it. Maybe you video record what you're doing. Maybe you just copy it down. And this can allow for easier reproduction when a bug emerges, especially if you're going, 10 steps, 20 steps into the system, trying different use cases, then suddenly it blows up. You want to kind of be able to know how to recover where you were. Does that make sense? Okay, so a key thing that I want to point out here is that I don't know how much you folks are aware of it, but the past few years have witnessed a revolution in terms of the growth of not just earlier than that sort of virtualized servers and virtualized mechanisms, but containerization. And tools like Docker, Rocket, and others, Kubernetes systems for running scalable, large-scale containerization, these are taking the world by storm right now. And one of the reasons that they're taking the world by storm is that they're a key asset in terms of testing and ensuring reproducibility and ensuring comparability between, say, a dev environment and a test environment. So that developers can be testing their software in precisely the same conditions as testers are using it with, or so that we normalize for the different platforms involved. So you may be using a Mac, I'm using Linux, but we can test it on an even keel. Another issue is the whole ability to reproduce the environment. So with a container, Dockerized container, you can set it up to output, to persist data to certain types of information if you want to. If the processes inside of it need to write to a place, you can configure the Docker container to be allowed to write to certain places. But by and large, the image itself is going to be reset to its original state when you restart the container, okay? And what this means is that you can set up a container that might have a Postgres server running in it. It might have a set of information in files associated with configuration or what have you. You could use this container to go through a set of tests, to prepare test procedures, execute them, evaluate whether they've worked correctly, log to some external resource through container permissions. And then this restore is just a totally straightforward thing because the container remains unchanged. And so you can executed again. And you can hand this container off to someone, right? Or more likely they already have access to it. Someone on the test team or someone on the dev team to show how the error got reproduced. So instead of dealing with issues where like I'm on a Mac, you're on a Linux machine, and you can't see the error that I'm creating, I can hand it off to you. Yeah.
So I know there is a difference, but I don't quite understand it. The difference between just a VM and then a container. Yeah.
So there's a lot of different layers to this. Generally speaking, a VM like you might run in VMware, might run in VirtualBox, other environments out there. It's going to be running in a way that is typically more like simulating an entire machine from the ground up, and it is far less lightweight. It's far more heavyweight in terms of its computational requirements than a container. Okay, in a container, you are running. It's true. You're running Linux, say, in this container, or you're running Windows, but it is, in terms of the computational effort required to run the container and the amount of the container size and resources to run, it's orders of magnitude smaller typically. So you can have containers that are shipped around, for example, that might be 80 meg or something like that, that actually capture a lot of functionality there. Another thing that a container will give you is the ability to specify what it builds on top of. So you have in these containers layers associated with different levels of resource. And a container can, for example, extend other containers out there with additional resources, which allows essentially the machine on which you're running to either use as it were, a cached version, or go down and download more resources as needed from a certain site. So the actual container specification can be quite small, and it actually just sort of picks and chooses which things to pack up in it to undertake its actions. And as such, it's a lot less load than having like a VirtualBox image on your computer where it takes up, hundreds of gigabytes of space or something like that for a complete definition of the system, and it just stays there. Rather, with the container, you can kind of mix and match different existing containers, which can be obtained through common sites. So there's a Docker site that you can go download containers for all sorts of things. More to the point, well, also important, containers are sort of configured in a way that allows you to set in a very tight way the permissions they have to access things like network resources, disk resources, etc., which is normally different than how we use virtual machines. Like if we use a virtual machine, we have a standalone Windows virtual machine or a Linux virtual machine. We can run it. It has its own resources, yes, internally, but normally we don't specify as a key part of it. It's only allowed to go to these resources externally. It's only allowed to access the network in this way or these network paths or whatever. Whereas with a container, we can nail things down to what it's allowed to access and how it's allowed to access it in a way that's tighter. There's also some issues, and I'd have to go review what the issues are there. But I think in terms of the process architecture for running the container, my recollection is that running the processes in the container requires quite a bit less overhead than in a VM, in a virtual machine. Okay, so I think with a virtual machine, there's limits to what you can do in different threads or what have you that in a container is lighter weight. But I'd have to double check my memory.
So in a container,
Yeah.
can you simulate a different operating system though? Like if I'm running Ubuntu, I can have a container that's Windows without any of the open.
You can have a container for certain operating systems which have been containerized. And those you could build the top of. And so I might be running Windows and I have an Ubuntu container, which, but it's generally not going to be all, everything in the Ubuntu standard distribution or something. It might be a real subset. And this is why containers are more svelte. The actual container specification is a text specification, if you look at it. But it specifies use like this minimal Ubuntu image and Postgres image here and layer in, this mechanism for Apache or what have you. And all that comes together. And people have created these containerizations for different subsets, but it's a much smaller subset than if I just installed Ubuntu from scratch. If that makes sense?
Yeah.
Yeah. Yes, but yes, it will run an OS as part of that.
Docker's free.
Docker's free. Yeah. And it's not the only containerization system out there, but it's the dominant one. Anyone else want to comment on that? Yeah.
A big part of it too, just the mentality about containers. They're made to operate as a slave device to whatever's controlling it, whereas a lot of VMs are kind of supposed to be their own thing or their own host. Containers just one job, one thing, and it'll go away once it's been used.
Yeah, so ephemeral. Yeah.
One more thing, I was talking to someone about it, and they said if one of the reasons for using containerization is that if it does crash or one of these containers does crash, it won't cause like a kernel panic in your actual computer. Is that true?
Yeah. Yeah. So yeah, I mean it can crash and it can exhibit problems, but it won't cause your system to go down at all. It's a very self-contained thing, and once it's gone, like, okay, so another thing with VMs that I should mention, it's a different mindset. Like with so I run, I don't know if you folks know, when I have to do PowerPoint, I use Windows VM. So I have that spun up on my machine some of the time. And, there, I have shared paths with my Linux box, but typically the Windows machine is undergoing state changes between times. So, I fire it up and it's storing away information in its temporary folders and in various folders within it. And, I may suspend it. I may save it away and come back into it, but I expect that change state to still be there. Whereas with a container, with the exception of anything that it's writing to external dependencies, like external drives that you've given it permission to access or whatever, it goes entirely back to its original image state. So when I run it again, it is precisely the same with respect to its image as before. Whereas that's very different from a VM. That's very different from a VM. You're kind of expecting it, with exception, you're expecting it to kind of be changing over time. So you don't necessarily have reproducibility. I don't know if that helps, but yeah, that's part of it. Okay. So great question. And I will say that containerization is proving so important in software engineering, but so important more generally in system management and just how we maintain infrastructure now. It really is worth investing in learning. Did they cover containerization at all in 332? Anyone know? Or 432? Did you encounter systematic coverage of containerization in any of your other courses? No. Okay. Possibly I might do a module on it late in the course then, and sort of where I talk about it more, because it's very, very important. So problems with reproduction of bugs. These are real issues, and with a lot of the communication challenges and sometimes acrimony between testers and developers have to do with inability to recreate things. And there's a lot of frustration that can come up with this. And it leads to bugs sometimes sitting that aren't fixed for much longer periods of time. So one of the major issues that's traditionally bedeviled software development is that testers and devs, and even more so, developers and testers on the one hand and users on the other often have very different environments. So if you're a developer, the classic anti-pattern to avoid here is development on Windows. Development on Windows in, at least for many years, and I must confess, I haven't been following it very closely since Windows 10, but for many, many years, basically if you were a developer on Windows, you were doing a lot as administrator. You were doing a lot of work as administrator because you have to write to the registry to register components, and you have to set permissions for areas or what have you in ways that required you to be administrator. And meanwhile, you ship your code out to users for whom administrator access is rare, and the exception rather than the rule. And they may have to ask an IT person to come by to get administrative access to their machine, and it takes a week to get that person by. And code that works just fine on your box does not work at all on your user's box. This is quite common in the Windows world. I would hope that's been straightened out in recent years in Windows, but I know it was a real problem earlier. Beyond that, there's issues with your box has probably more memory, more disk space, faster network, etc., than your average user in many cases. If you're doing app development, maybe you have the most recent version of iPhone or Android phones around, and meanwhile your users may be several versions outdated. And you can't blame the users for that. Those are the profiles of the users, but it leads to things that you don't see that they see, problems that they have that you don't encounter. And one of the best ways to normalize for this is to use containerization. To have a containerized environment that simulates a lower-end user experience or lower-end user machine context in which you can run then test code, and you can run and you can see exactly what they experience with the container. Okay. So that will help reproduction a lot compared to having different environments. Okay. So use containerization there would be my strong suggestion. I will note that per Owen's question here, I should have mentioned another big difference between containerization and virtualization that makes this use containerization more than an empty suggestion is that today, a growing number of continuous integration pipelines, including that, for example, on GitLab, support very easy containerization as part of the continuous integration output. In other words, they compile to a container, which can then be deployed and used. Okay, and so you're not going to be doing that with a virtual machine normally. That you're compiling to a virtual box, which is then used. But it's very common for containerization. So actually, your build process, if I can make it just using very plain words, your build process outputs a container that could then be used for testing by developers and testers, etc. That would be on the common page. And that's something which can be done in part because containers support specification in a way that's much more amenable to piecing them together and high-level specification in the form of textual description of what's in that container. There's many other issues with reproduction of bugs. You've forgotten some external details. You did something unintended and forgot it. You left the machine for a while, and it was able to. And during that time, something else changed. The time changed, or what have you. Maybe you've changed time zones before the issue came up. You started the program in one time zone. You went to another time zone, and that triggered it. And that's not being done here because you were in a mobile context and you have an issue with this. You can also have resource dependencies. Your machine has this extra drive or this extra higher speed network, etc. And you have different hardware. So there's a lot of different a lot of different reasons why reproduction may be a problem. Containerization can help with many of these by leveling, making sure that you have the same reference as in both the test and development side. Okay, I'm just going to go through this. The last thing I want to mention today is something related to traceability. Software engineering projects, we deal with a lot of different artifacts or processes. Okay? We deal with requirements documentation, specifications, sometimes vision documents, high-level summaries even before that, design documentation, test documentation, code, and test cases. The test documentation might be things like test matrices, might be things like that very nice diagram. Was it Team 4 did? Very nice diagram of sort of system function, how you can get from one part of the system to another. My heart leapt when I saw that. My heart wept when I no. nothing made my heart weep. Yeah. Okay. So these things are related. They're not isolated from each other. So a test case might be documented in test documentation and might in turn depend on testing a certain feature of the design that depends on a couple different requirements that need to be met. So the point is there's hidden dependencies between these. And a change in one, like if I change the design because I discover a flawed thinking about this aspect of the design, or I change requirements, so the user changes the requirements, right? The client changes the requirements. It ripples through to these things, right? So these things are related to each other. And we talked earlier about some ways of capturing this. We talked about test matrices, right? Right? And some of you showed me test matrices on Tuesday. And my heart stirred. Okay. We want to be able to fundamentally deal beyond documenting the relationship with one another. We want to be able to deal with change. So if one of these elements changes, we want to be able to map it through to changes in the other elements. And we want to be able to do so quickly so that we're not just knocked in the head with it. So traceability is this idea of being able to document one thing depends on what. So when you have a test case, what element of the requirements or the design documents is this depending on? Right? Like, what is this testing? What elements is it caught up with? Or where is this documented in the test documentation? What code does this test? You know, if it's a unit test, what thing does it test? So the basic idea here with traceability is, look, try to capture, try to describe, try to make explicit the interrelationships between these where possible. Try to make it clear, okay, these test cases, they test which code. That's an obvious one, right? But the code, which parts of the design or the requirements is that implementing? Like what's the relationship to those things? This should be something which allows you to then respond more quickly when there's been a change. Because if the user changes a requirement, the client says, you know, we're going to actually change this side of it. You know then which code is affected. You know which tests are affected. You might have an understanding of which elements of the test documentation need to be changed. And you can react in a proactive way to that rather than waiting till those things strike you later. Okay. So see in your documentation if you can characterize something about what depends on what, so that when these things change, and they'll change even in incremental development sometimes, you can propagate those changes down. Okay. Okay. That's all we have time for today. Thank you very much. We have a set of material we'll be covering next week in different areas before we go deep in the testing side. Thank you very much.
Where?